The driveline includes the components that convert a truck's engine power and speed to more usable combinations of power and speed at the wheels. The first unit in the driveline is the transmission. And at first glance, a truck transmission is a pretty awesome thing to see. Actually, though, a transmission is nothing more than a series of gears and shafts designed to deliver a selection of power and speed combinations to the rear axle. Any basic truck transmission contains 4 shafts. The first of these is the input shaft, which brings power from the engine and clutch. We've colored some of the teeth yellow for easy reference. Next, there's the counter shaft, which is driven by the input shaft. Note that the counter shaft drive gear also has yellow teeth. The next shaft is the reverse idler shaft, which rotates with the counter shaft. Finally, there is the main shaft, which delivers power from the transmission to the rear axle. The main shaft seems to be connected to the input shaft, but a close-up view shows that it rotates freely in a bearing inside the input shaft. These 2 shafts are locked together only at one special time, and we'll get to that in a moment. So this is our basic transmission shaft setup. But you'll note that even though the input shaft, counter shaft, and reverse idler shaft are turning, the main shaft is not moving. We need more gears. For clarity, let's remove the reverse idler temporarily and shift our view, so we can more easily see the forward speed gears to be added. To start, we add first gear to the counter shaft. The color coding of its teeth is light green. This gear is press-fitted and keyed to the shaft, so it always turns with it. We match this gear to first gear on the main shaft. It's also light green. Now, since these gears are always in mesh, we call this a constant mesh system. However, as you can see, the main shaft first gear is turning freely on the main shaft, while the shaft itself still isn't moving. Here is how we tie this gear to the main shaft so we can deliver output power. The main shaft gear has a second set of teeth facing inward. You see them when you look closely. These teeth mesh with a component called a sliding clutch, which we will add onto the main shaft. The sliding clutch has teeth on both its inside and outside diameters. The inside diameter teeth constantly engage the spline on the main shaft so that the sliding clutch always rotates with this shaft. To shift into first gear, the sliding clutch is slid along the main shaft until the outer teeth of the clutch engage the inner teeth of the main shaft first gear. This action locks the gear to the shaft. Now the gear train is complete. Power from the engine drives the input shaft. The gear at the end of this shaft drives the counter shaft drive gear, the yellow-coated gears. The counter shaft low gear, coated light green, drives the main shaft low gear, also light green. The sliding clutch has locked this low gear to the main shaft, so the main shaft is now turning, and in the same direction as the input shaft. However, as the yellow lines along the main shaft show, it is turning much more slowly than the input shaft. Here's why. Since the counter shaft drive gear is larger than the input shaft drive gear, the counter shaft turns more slowly than the input shaft. The counter shaft low gear is smaller than the main shaft low gear, so the main shaft turns more slowly than the counter shaft. This combination of gears gives a high torque or turning force out of the main shaft, but low speed. In other words, a typical first gear requirement. For added speed, we must change gear ratios. First, we add second gear to the counter shaft. This one is coated in blue. This gear, like all other counter shaft gears, is permanently locked to the counter shaft, so it always turns with it. Then the main shaft second gear, coated blue, is added. Since this is a constant mesh transmission, main shaft second rotates with counter shaft second at all times. However, main second has not yet been locked to the main shaft, so it turns about it freely. Only first gear is engaged. To lock the main shaft second gear to the shaft, we again add a sliding clutch, this time to the left of main shaft second. In this particular transmission, all sliding clutches are the same size and shape. Let's move in a little closer to watch the shift action. To shift to second, we first must disengage the first gear sliding clutch and then engage the second gear sliding clutch. Only one sliding clutch can be engaged at a time. Otherwise, we'll be trying to drive the main shaft at two different speeds at once. The clutches are moved by what are called shift forks. You can see them extending upward from the center of each clutch. These forks are moved back and forth in proper sequence by the driver's gear shift lever. Looking at the overall system again, we see the shift has been made. First gear is disengaged and second gear is engaged. Now, with the input shaft rotating at the same speed as before, the main shaft speed is increased because there has been a change in gear ratios. Now we continue to add gears to complete the transmission. Third gear, which is coded in red, is to the left of second, and we see it uses the same sliding clutch. First, the clutch disengages second, then moves to a neutral position where neither second nor third is engaged. As it continues to be slid to the left by the shift fork, it engages third, so the transmission is now driving in third gear. Fourth gear, coded green, and fifth gear require adding another sliding clutch, which works just as the others do. In this transmission, fifth gear is direct. This close-up view shows how the sliding clutch shifts to lock the input shaft directly to the main shaft, so both now turn at the same speed. The counter shaft is simply idling. Note, though, as was mentioned earlier, that all gears are turning. This is characteristic of the constant mesh transmission. Remember the reverse idler shaft? To illustrate how reverse works, we have put the reverse idler shaft back in its proper position. Then we add reverse gear on the main shaft. It's tied to the shaft by the same sliding clutch that's used for low gear. Now power comes through the input shaft to the counter shaft, to the reverse idler shaft, to the main shaft. By adding this extra gear, the reverse idler gear, to the gear train, we reverse the direction of rotation of the main shaft. The input shaft and main shaft are now turning in opposite directions. This enables the driver to back up the vehicle. Notice the gap between the gears on the counter shaft? Let's add one more gear to this transmission right there in that gap. In this case, there is no matching gear on the main shaft. That's because this new gear is the power takeoff gear. Since this gear is keyed to the counter shaft, it is always ready to provide takeoff power when the counter shaft is turning. So here we have a more or less typical transmission. Differences between this transmission and others are primarily in design details. Now, how about the Fuller twin counter shaft transmission? That's simple. All we do is add another counter shaft on the other side of the transmission. Actually, we built up the sample transmission using one side of the Fuller T905. Here's the thinking behind using the two counter shafts. When one gear is driving another, only the 2 or 3 teeth actually in contact are transmitting any power. Teeth not in contact are sort of going along for the ride. By adding a second driving gear on the other side of the driven gear, we put teeth on both sides of the driven gear to work. Thus, the load carried by each gear tooth is cut in half. With the load reduced, gear face width can be reduced. For example, at the right is a 900 pound-foot twin countershaft gear. At the left is a 690 pound-foot gear for a single countershaft transmission. The twin countershaft, by splitting the load, reduces both weight and length of a transmission. Here is our basic transmission with something new added, an auxiliary transmission. An auxiliary transmission is used to multiply the number of output speeds available to the rear axle without adding a great many more gears. This is a 2-speed auxiliary. It doubles the output speeds available to the rear axle by providing either a direct drive or an additional low-speed reduction to main shaft output. Right now, the transmission is in neutral, so the output shaft at the right is not moving. When the auxiliary is shifted into direct drive, output from the main transmission travels straight through the main drive gear and sliding clutch of the auxiliary transmission to the output shaft. The yellow tape on the auxiliary output at the right side of the picture shows it rotating. In low-speed drive, output from the main shaft travels through the main drive gear of the auxiliary, through the counter shaft and the low-speed gear and sliding clutch to the output shaft. Notice how the tape indicates the output speed is now much slower than before. Let's move in closer and talk about shifting. Shifting in the auxiliary is also done by a sliding clutch. You can see the groove where the shift fork fits. But the shifting action is somewhat different from what we have seen because a new element has been added. This clutch utilizes a mechanical synchronizer to do the job of matching output shaft speed to main shaft speed before shifting, an operation which in the main transmission is controlled by the skill of the driver. Let's take a look at the sliding clutch and synchronizer assembly. In the center of the assembly is the sliding clutch, which is internally splined to the auxiliary transmission main shaft. The brass components on either side of the clutch are the synchronizers. When a shift is started, the brass synchronizer contacts the gear into which the shift is to be made. It rubs against the gear, kind of like a brake shoe, and by frictional drag, matches the speed of the sliding clutch to the speed of the gear. If we disassemble this unit, we see that each of the synchronizers incorporates 3 pins called blocker pins. These blocker pins block the clutch from engaging the gear until their speeds are matched. Result, no grinding of gears during shifts. Let's return to our main transmission. As we mentioned at the start, while there may be design variations and special features, some of which have not been covered here, all mechanical transmissions incorporate the same basic components. An input shaft to deliver engine power, a counter shaft which is turned by the input shaft and which contains a series of gears to drive the main shaft. The main shaft itself, on which are mounted matching gears which are driven by the counter shaft gears to provide a selection of gear reductions. And a reverse idler shaft, which permits introducing another gear into the gear train so main shaft direction of rotation can be reversed in order to run the vehicle backwards.